Hello, my name is Thomas Elliott from CryoSentinel. We have an experiment today where we have a vacuum flask. We're going to be pouring some liquid nitrogen into that vacuum flask, and then we're going to be drilling a small hole into that vacuum flask and watching the thermodynamics through the CryoSentinel and monitoring the temperature with the temperature probe there. So we have our liquid nitrogen. We can see immediately it's extremely cold, minus 196 degrees Celsius, showing up as very, very dark blue or even black through the CryoSentinel. The color is compensating here. We have a lot of yellows, whites and brighter colors to compensate for that extreme cold. We're now going to get an approximate depth of the liquid nitrogen by using a wooden stick. We can see there's a good amount of liquid nitrogen in that vacuum flask. We will now take the thermocouple, which has been inserted through the lid. We can see it's about 23.6 degrees there. And as we put it into the vapor phase of the liquid nitrogen, we can start to see the temperature drop down. We continue to see that temperature drop down, minus 60 degrees. It's not a rapid drop in temperature because we're not inside the liquid nitrogen, but it's slowly equilibrating to that temperature. We're going to skip forward a little bit until we're at temperature. Okay, so here we are. The temperature has dropped down to almost minus 170 degrees Celsius, and we're going to get our drill and start to see if we can make a hole in this vacuum flask. It's actually trickier than you may think. We have a drill here, cordless drill. Keeping an eye on the temperature, keeping an eye on the flask here. So it is important to remember here that this is just a small, cheap vacuum flask. It does utilize a vacuum in very much the same way that the liquid nitrogen Dewars will have a vacuum, but the thermodynamics between the two systems are very, very different. But it will give you a good idea of how things react with the liquid nitrogen in the system if you remove the vacuum. So as this experiment progresses, keep an eye on that temperature, but also look at the overall thermography as portrayed through the CryoSentinel, as it represents different temperatures through the different colors. Temperature down, minus 170 degrees now. And there we go. We can immediately see the vacuum flask cooling down there. You can see the internal temperature is actually decreasing lower than minus 170 degrees, minus 180. We're down to minus 190. We're heading down to minus 200. This is a thermocouple. It's not going to be extremely accurate, but it's going to give a very good representation of the temperature. So we've made the hole in the thermos flask. We've introduced heat into the system, and yet the temperature has got even colder down to the temperature of liquid nitrogen. So what's happening here? When you make that small hole and you lose the vacuum, there's a massive change in energy as the room temperature air comes in contact with the inner metal of the vacuum flask. That is dramatically and rapidly heating up the liquid nitrogen. The liquid nitrogen then boils and turns into vapor phase nitrogen. When liquid nitrogen boils, the expansion ratio from liquid to vapor phase is about 700 to 1. So there's 700 times the amount of volume in the vapor phase. This huge expansion is forcing out supercooled liquid nitrogen vapor out of anywhere that it can escape from. So now we have supercooled liquid nitrogen vapor in our system, much colder than regular vapor phase nitrogen. And this is one of the reasons that immersion probes in cryogenic Dewars don't work in the event of catastrophic failure.